give you real numbers instead of, let's see. So the, yeah, 6K and change. So it's about 6K. And if you strip out the names, because the program still works, if you collapse the names out of it, then it's about 3K. So what does it do? Let's see. So by default, it gives you this big poof of stuff, which is not all that interesting. But I can change the mode and turn it into something where there's a simmering fire, or I can turn it into a. Use that for the fireside. Yeah. So you can change it into this sort of a fountain of stuff. I can turn off the trail, and then it sort of sputters out and can make it wiggle and disperse and sort of all kinds of fun possibilities. So
and you could also apply this to galaxy collisions.
Yeah, no. So I had hoped to get to sort of more interesting. So right now the particles are not actually interacting with each other. They're just behaving under certain constraints. But yeah, exactly. But the next step obviously would be to implement one of the different approaches for having them interact, and there's all kinds of fun opportunities there. So it is a 3D. That's the other thing I should mention. The way it's done. So there's a 3D space, but it's actually just an orthographic projection. So it's just, and I did it actually. I should mention with fixed point, and it's drawn in a blending mode where I'm drawing with a sort of an orangish color, and it's going into an RGB buffer. And so as they're being drawn, you can kind of see it. If you watch very closely on the edges, there's kind of they're being drawn as little rectangles that are mostly translucent. And so when a few of them overlap, you get kind of an orangish, and as more of them overlap, eventually you saturate out first the red and the green, and then you get kind of a yellow, and then eventually it gets to a white as it completely saturates, because there is a little bit of blue in it. So any questions?
Wow. What do you think be the uses for it, the best uses?
I don't know. So to be honest, I partially did it as an exercise in convincing myself that the sort of it's funny to call it sourceless given that there's source code, but the quasi-sourceless approach made any sense. My biggest worry was performance with that, and so I think I've been surprised actually. Now I'm dying to remember. I don't remember with how many particles. That was 20,000 particles, but let's see. How does it behave if we do 200,000, for instance? It's not slower, but not,
Well, this should give
yeah, so it's
pointer resolution.
Yeah.
Which you can see it is.
Yeah.
Multiple explosions.
I was changing the mode as it was going, so it's sort of which effect. Yeah. So I'm changing the physical. Actually, the mode influences two things. It changes some of the constraints the particles operate under, and it also a random subset of the particles get reset and brought back to the start point based on it. So it's not that's not that. It's certain. So it's at least linear in the size of the things. But anyway, so that's a good question. So I think I might. I think this has inspired me to believe that this could be made fast, which makes me think it might be a good approach for sort of future forths. I'm especially curious to try what it behaves like when I swap out the bytecode interpreter for machine code. But I think what I probably will do first, part of why I started with the bytecode interpreter, is that I will probably want to also experiment with what does it look like to have an editor written that can edit this representation in memory, because it's something that I'm doing the disassembly in C because it was convenient. I had the X macros to do it, but it would probably be straightforward to do in Forth as well.
Have you looked at Jeff Cox's AHA Forth, which is
I-
also a sourceless Forth?
Yeah, I have looked at his document on it. I didn't know if there's is there actual material about it? Oh, is it? Okay, I should. I've seen it in the past, and it's been a while since I looked back. I'm trying to remember what his approach was to some of these issues.
Yeah, he has some. I think it's like. Yeah, I'm still trying to make sense of it myself.
I think to me, the sort of aha moment, as it were, was that I had been in my previous attempt. I had the symbol table in ELF, and so I was actually using ELF, and I actually went so far as to I have a program where it sort of expands itself out. So it starts out with the dictionary and everything in the tightest ELF file you can have, and then on startup it does the maneuver of like, let me separate out the string table so that the dictionary has room to grow, and you can conceivably change it. But what kind of stopped me in my tracks was it was so complex by that point. It was like I was doing all of these maneuvers just to be compatible with ELF, and it didn't feel like I was. Whereas what I find appealing about this is that you've got a stream of stuff that is just machine code or bytecode, and then you're just embedding information or knowledge in that, and then
You have to use the dictionaries or the stacks as a gap buffer or a zipper of sorts, maybe?
yeah. I think to me the biggest quandary is what the relationship is with like where is there a dictionary, or is it just sort of this tagging related to it? The variables I'm not very happy with, because what I end up doing for words, you have a call. If it calls to a certain location, you assume that the name is sitting in front of the call site. But for variables, I didn't want to put I didn't want to reference the memory location directly, because if this was sitting physically in a code page, that would be problematic in terms of cache. So I'm sort of torn. In a classic system, it would actually kind of have made some sense, but in a contemporary system, it doesn't seem like a good choice. So instead, I have a series of definitions of variables, and then they number the space of variables. But that feels sort of weirdly indirect. And
Yeah.
so, anyways.
I have to apologize. We dropped a portion of your talk. Wi-Fi.
No worries.
Out.
So is life.
It's life. You'll have the slides eventually.
Indeed.
Yes.
So. All righty. Thank you all.
hopefully I have audio. A, B, C, D, E, F, G. Cool.
Gotta have a little bit of break between words. Tell. Small as a marker.
Hi, I am.
There you go.
Okay. Hello, I'm streaming, right? I am streaming.
Oh, you are streaming.
Excellent. Thank you.
Sure that everything's alive, and yes, we're fine.
Awesome. So my name is Sam Falvo. Been working on the Kestrel project now for many years. Fairly recently, within the last year or so, I actually finished implementing the first RISC-V processor in Verilog for the Kestrel project. It's an important qualification because I'm certainly not the first person to do a Verilog implementation of RISC-V, but this is the first one that I've made for my project. Along the way, I have had certain assumptions about the computer which were inherited from the Kestrel 2, its predecessor, which did not turn out to be the best assumptions to make going forward. So there were some lessons that were learned, not all of them good, not all of them bad, but I figured I'd select what I thought was a broad cross-section of lessons learned from working on this project. The first lesson learned is if you're working on an open source core, by which I mean a Verilog module that you can use in an FPGA design, it's probably best to go with a number rather than a name. So the CPU went through several different names. I'd long forgotten the original name that I picked for it, but the penultimate name for it was Polaris. That lasted me for about a year. But it turns out that even that was not a good name because, well, all the names that I've picked for this processor had trademark infringement issues. Without exception, every single word that I've picked in the English language has at some point been used by a competing or potentially competing organization or industry and has been trademarked. And this last one by AMD is particularly egregious because a CPU and a GPU are in the same market segment, which means that AMD, if I were to release a Kestrel 3 with the processor core named Polaris, AMD actually has legal grounds to sue me. Not even a cease and desist, just full on you're served. So the solution to this is to go back in history and look at what Intel did back when they were about to release the 80586. Oh, you don't know about the 586? Well, that's because Intel renamed it to the Pentium. And the reason they renamed it Pentium is because Intel and its competitors could not trademark the number 80586 because 8086, 80186, 80286, these all had become so commonplace in the market that attempting to trademark 80586 failed flat on its face. Trademark office wouldn't have any of it. And Intel was like, nope, we can't have that. So they switched from using numbers to names. And ever since then, if you look at video cards or if you look at audio cards or pretty much any kind of peripheral on a PC, yeah, they all have model numbers and stuff like that, but they all belong to a family with a well-defined name, and it's always trademarked. So what I wanted was just the opposite. I wanted to go back to a place where it was nigh impossible for someone to try to tell me to cease and desist. In other words, I wanted a number. I wanted a part number. And so I came up with KCP 53,000. That number, of course, has several inspirations. KCP, obviously, Kestrel Computer Project. But the 53,000 was kind of a, excuse me, kind of a throwback to the 68,000 or the 6502 or the 1802. And if you look at all these popular numbers, people, these numbers that have marketability to them, they always have between 3 and 5 syllables to them. So I picked a number that similarly had 5 and 3 syllables to them. So the lesson here, of course, is if you want to work on an open source project and you need to be proactive in avoiding legal issues, I recommend using numbers, not names. Premature pipelining, you should avoid it. This is basically a hardware case of premature optimization. Ideally, you'd want to get your processor or whatever it is working, even if slowly, first. So you want to, like I said, build a slow sequenced working implementation first. Get all the logic that you need to implement in, because when you pipeline the thing, all you're doing is inserting flip-flops in between the logic anyway. So if you have your sequence working implementation, that's less for you to debug because the actual logic is there. When I first started working on this, I didn't follow this advice at all. I figured everybody else is just working on pipeline processor implementations from scratch, so I figured I should be able to do it too, right? I don't recommend it. I'm not going to say it's impossible for people to do, but I found that the complexity involved near hockey stick levels of complexity. There was no way I could keep the design scope in my head all at one time. So premature evil is the root of all optimization. This is a deliberately backwards reference to the original quote by Donald Knuth. Why is it premature evil? Because you're greedy. And why are you greedy? It's because you always want to do the fastest, smallest, coolest implementation ever. Don't be evil. Don't be clever. Cleverness is always evil, right? So stay simple and then optimize later. So the 5th attempt is finally successful. It is technically a 2-stage pipeline, but I'm actually alternating the 2 stages in time. So in effect, it's not being pipelined, but it is structured like a pipeline. It is a PLA-based sequencer and decoder, just like the good old 6502. Instruction fetch and execute currently take turns, like I just said, although it is very simple to alter the PLA code to get those 2 to run at the same time. Another aspect with respect to pipelining, and another reason why you should avoid it, is because all the research documentation that I have access to, that is to say, which is not behind a paywall, they always document pipelines as being this waterfall of data flow, from fetch to decode to execute to memory to write back and then to the bit bucket after that, because there's no further stages. But the reality is there's a whole mess of control logic that they don't show you there. And this control logic, by the way, is the cause for the hockey stick complexity. It's very easy to do fetch to decode from scratch in a pipeline. That's trivially simple. Decode to execute, not so much, because that involves register fetch. It also actually involves register write back, believe it or not. And if you have an interrupt, then you need to have the control structure that clears, that blows out all of those pipeline stages. So this is what it actually looks like. So you have your usual pipeline steps here, but then you have this wrapper of control logic that wraps all the way around. And it also mediates access to the register file. But at the same time, your fetch and decode consists of separate memory channel than your execute and memory stages to external memory. So you have all these different ports that are all active all at the same time, and you have to coordinate that. Your control logic is the way to do that. And typically it's represented as a big blob, as I do here, which is actually how it is implemented in the current CPU, but it could also be implemented as nested state machines. And this is part of the reason why things are so damn complex, is because it's nested, and you have to like sequence, you have to sequence the very state machines that are implementing their sequencing. But the one advantage to doing it this way is by separating out the control logic and actually making it a visible part of the design, is it makes refactoring things much, much easier. So like right now, as I mentioned, I have two stages of pipelining in the CPU. I've got an instruction fetch, and then I've got decode, execute, memory, and write back, all in one big blob of logic. And this is all mediated by separate state machines off in this separate area here. But if I wanted to, at some point, optimize this, it would be very easy for me to say, okay, let me separate out decode logic and then just leave execute, memory, and write back as a single blob, and then later decompose that, right? I can do this recursively, and it would be much simpler and easier to go from this 2-stage to the 5-stage design without affecting too much external circuitry. In fact, the external circuitry won't even know the difference. So that's another reason why it would be ideal to not prematurely pipeline. But you do want to pipeline eventually, right? So there are opportunities for optimization. If I overlap instruction fetch and execution, I get between 60 and 100% improvement in performance. So right now my target design speed is 6 million instructions per second. If I make this one very simple change, this one cheap trick, if you want to call it, give it a clickbaity name, that will effectively double performance to 12 MIPS. If I were to double up the block RAMs that are backing the register set, so that I can access both registers, both source registers at the same time, that gives me between 25 and 33% boost in performance, assuming that I'd already overlapped instruction fetch and execution. Assuming that that is the case, I can overlap instruction fetch and register write back. That will give me between 30 and 50%. So basically what's happening is if I overlap instruction fetch and execution, I basically save 2 cycles out of every instruction that executes, and then perform both register fetches, that's another cycle saved, and then the register write back is another cycle saved, right? So we go from 4 cycles down to 1 cycle. And of course, these compound, of course. So given the same 25 megahertz clock, we go from 6 MIPS all the way up to between 16 and 24 MIPS, depending on the instruction MIPS. So Furcula bus is my own interpretation of the Wishbone bus. It is not compatible, but it is designed to be easily bridged. And I'm actually quite pleased with it. I have one design mistake, which I will be fixing eventually, but it is as I said, it's a fork of Wishbone B3. It uses justified data transfers. So in most buses, you have byte lanes. So a 32-bit bus, for example, will have D0 through D7, D8 through D15, D16 through D23, and so on and so forth. And then a set of byte enables that says, okay, which subset of these bits contains a valid byte. Furcula doesn't work that way. Byte traffic always goes over D0 through D7, period. Half-word information always goes over D0 through D15. The way we indicate which portions of the bus are used is we export a size tag that indicates if it's 8, 16, 32, or 64 bits wide. I do expose a, excuse me, I do expose a signed bit, which is used by external logic to perform zero extension or sign extension as appropriate. But in all other respects, it's actually equivalent to Wishbone B3. So this is here I'm illustrating if you want to address different bytes within a single 32-bit word, how the byte lanes work with respect to half words, bytes, and full words. And this is the equivalent justification approach. So the reason why this design was chosen is because it actually results in less traffic, or I'm sorry, not less traffic, but less complex logic in the hot path of the processor, which allows it to complete things much more quickly. This is actually, how can I put this? This is based on an observation that buses always outlive the CPUs that spawn them. So for instance, Intel CPUs nowadays, ever since the 8086, they pre-decode the size and the lower address bits to break data into individual byte lanes. And this started with the byte high enable on the 80286. But the individual buses that these chips connected to, you can actually still find them today. You can actually still find the ISA bus today. It doesn't really go by the name ISA, it now goes by the name PC104. But let's be realistic, it's the ISA bus. So supporting legacy buses actually requires resynthesizing information from the byte lane enables and the missing address bits. So in effect, you have external circuitry that undoes what the CPU tried to do to be convenient for you. So you have two chunks of logic that are involved with this, which nullify each other. So I figured, well, why don't we just not include that logic to begin with and just let whatever is responsible for connecting to that bus be responsible for handling this decode. And that's the motivation behind Furcula. The name Furcula, by the way, is Latin, I believe, for wishbone. So speaking of wishbone, there are two versions. One is Wishbone B3 and one is Wishbone B4. And a feature of Wishbone B4 is that it has a special pipeline mode. But before I go into explaining why I wish I'd gone with Wishbone B4 Pipeline, let me recap Wishbone B3. So if I want to make some accesses to memory, I can do it. Everything is always synchronized, as you can see, by the rising edge of the clock. And I can actually do a single cycle transfer if I can assert ACK, the acknowledged feedback, fast enough. Unfortunately, that's very rarely going to happen, especially if I need to make multiple back-to-back accesses. So in this case, if this is an access to a device and then this is an access to the same device, how does the device know whether or not it should respond within 1 or 2 clock cycles? Right, so you have to negate ACK in order for this to synchronize, and then you reassert it the following cycle once you're sure that everything's acknowledged. So this results, even though theoretically you can get 100% bus efficiency, in practice you can only get about 50%, which I kind of already summarized here. It's closer in scope to PCI than it is to AXI4, for example, in terms of overall economy. There are some conditions, as I indicated, that you can do 100% efficiency. If you use fully asynchronous slave logic, or you can somehow assert that act within 35 nanoseconds or less, assuming a 25 megahertz bus. And you can assert at least one address bit changes so that something somewhere knows that it's a different bus cycle. Then you can do this. So for example, if the CPU is accessing instructions in ROM, then accesses data, and then touches an I/O port, and then goes back to accessing ROM again. In that case, where you're basically spraying addresses across the entire thing, across the entire address space, you can get single cycle access pretty easily. But if you're doing cache transfers, for example, something involving burst mode transfers, it's not so easy. Bus bridges and adapters, of which there are numerous in the Kestrel 3 design, just adds to the propagation delay. You may recall that I said 35 nanoseconds is pretty much the effective limit. Kestrel 3 measurements seem to take 33 nanoseconds, and this is on a Xilinx device. So I'm coming awfully close to violating setup time. Not only that, but I've discovered, much to my great frustration, that it is demonstrably incompatible with the pseudo SRAM chip on the Digilent Nexus 2 board. I have to implement a state machine, which basically forces me to go from 4 clock cycles per instruction down to 6 clock cycles per instruction. I'm sorry, per memory transfer. So that would basically be a total of 12 clock cycles, because it's 2 16-bit transfers. So in order to improve the performance, we would need different clock domains, which would involve FIFOs. Now, FIFOs are easy enough to do, but the real complexity comes in the debugging of the asynchronous interlocks that are necessary to bridge the 2 clock domains. So B4 works very differently. So in B4, we notice that instead of stretching things out, we just jam addresses onto the address bus here. We specify, whether or not it's a read or a write. If there's output data, everything is lined up perfectly. And then the acknowledgments come potentially many clock cycles later. This does not actually hide the latencies involved with address decoding, but what it does do is it meshes better with how FPGAs work inside, because you've got a lot of flip-flops at your disposal, and you can use that to synchronize things. It also allows you to amortize the access time by grouping multiple accesses on in flight at once. And in that sense, it is closer to AXI 4 than it is to PCI. There are a little bit different interpretations on how you interpret the cycle, strobe, and acknowledge. I won't go into too much detail here. These slides are up online. Let's see here. But yeah, basically just what I said. So yeah, overlapping bus transactions. Kestrel 3 doesn't actually use them right now, but will eventually, especially once I get into DMA-driven channel I/O. Easier to synchronize across different clock domains by far, because you're basically reducing your interface circuitry to just FIFOs. There's little actual need for asynchronous interlocks as far as I can tell. And you can actually implement bridges using state machines much more conveniently as well. So for instance, if I want to support rapid I/O and hardware, that would be an easier thing for me to pull off. And that's pretty much it. Those are the 3 big ticket lessons that I've learned. There's my contact information. And does anyone have any questions? Yes.
I'm just going to say, for my class, students use a design development cycle where they start fast, start very simple with low cost, low resolution materials, and then build from there as they learn as they're going. So it sounds like there's an analogy here with what you've done.
Yeah, my mistake basically comes from what's a good I think the name of it is like second system syndrome or third system syndrome or something like that. Basically, I was cocky, is what it boils down to. Just because I had previously existing hardware for the Kestrel 2, my thought process was, well, I'll just build a new CPU and I'll build a set of bridges that couples the 64-bit bus down to a 16-bit bus and just plugs into the Kestrel 2 infrastructure, and then I'll optimize that later. That worked great for accessing the video, for accessing keyboard and general purpose I/O. But that failed spectacularly for accessing external RAM. It is amazing how, like, to this day, I still have not gotten external RAM to actually respond to a bus transaction. It doesn't even drive the data bins. I have no idea what's going on. That said, that's only one example of the cockiness. The other example, of course, was, like I said, seeing everybody else put up GitHub repos. It's like, oh, here's this XYZ CPU and it's got this 3-stage pipeline, or here's this ABC CPU and it's got this 5-stage pipeline. You never actually see the actual development process that went into these things. So I'm thinking, oh, okay, well, a pipeline is relatively simple to draw out on a piece of paper and to explain how it works logically. And other people are putting out CPUs that are, pipelined to some capacity. So I figured I'd do my hand or try my hand at doing the same. And that exploded with much fireworks and huge complexities, and just trying to get Verilog to work with that was just a royal nightmare. Cool, and that's it. Going once, going twice. Sold. Thank you very much.
Run out of things to say and do, and so until next month, goodbye.